welcome to our season finale of Extreme Reloading. In our last episode, we headed out to the range and shot both the 9mm Luger we've been working on all season long, as well as the 5.56 NATO that we've been working on all season long. Both of those rounds proved to be super safe and reliable ammo like we were trying to craft, and they both performed pretty darn well, having a nice single-digit standard deviations. Now, the one problem we noted was that the 5.56 round shot kind of off target. Actually, one round did hit or impact off this target here, and they shot, a little bit to the right. Now, the easy fix for this, since this scope is not zeroed currently for this load, a 62 grain Barnes TTSX, that's what we were loading. Simple fix for this is simply to shift the reticles so that the point of aim equals the point of impact. When that happens, we say that that rifle is zeroed for this load. But what's happening with this load out at 200 yards or 300 yards or beyond? In other words, I need to know something about the trajectory of this particular load. To do this, or to calculate this, I need to know a little bit about this particular load. And those things I actually already know. Number one, this load has an average muzzle velocity of 2,846 feet per second, and a very nice, as I mentioned earlier, 6.5 feet per second standard deviation. I also need to know something about the particular load's ballistic coefficient for that bullet. And I need to know, is that ballistic coefficient derived from what we call a G1 function or a G7 function. Now we'll also need to know things like the bore offset. In other words, what is the height of the sight, the reticles, let's say, above the center line of the bore, and at what range is this load zeroed for this rifle. Now we already said that's 100 yards. Now to make this a little bit more interesting, I'm going to go back and use the .308 Winchester load for our example today, simply because it stretches out viably quite a bit further than a 5.56 does. Now, in addition to ballistic coefficient and those couple of absolutely mandatory pieces of data that we need to calculate a trajectory, it's sometimes, or it's oftentimes useful to also know the twist rate of the rifle, the type of adjustments for your particular scope. In other words, does your scope have MOA, quarter MOA adjustments, sometimes half MOA, mil adjustments, normally a tenth of a mil adjustment, or sometimes on more of the budget line of scopes, value-based scopes, you'll see a adjustment of 1 inch, approximately 1 inch and 100 yards. The other two pieces of data that's very good, sometimes necessary to know based on the solver that you're going to be using, is what were your ambient environmental conditions when you calculated or measured those muzzle velocities. In other words, particular importance is the temperature, humidity, barometric pressure can sometimes be asked for, requested in a solver type of software. What was the elevation that you were shooting this at, the altitude, and sometimes also the latitude that you were shooting at. 45 degrees north latitude, 42, 48, whatever, that sort of thing. With all these data in hand, we can now use a ballistic solver software. Sometimes those ballistic solvers are strictly and online, and those are great, they work out very well. Other times it's a piece of software that you have installed on your computer. Now, years ago, I started early on using JBM ballistics. Also used Ballistech that I actually wrote a number of years ago. And more recently, I've started using a very well created spreadsheet called Ballistic PRS. And then there's also Shooter's Calculator, an online site that you can use to calculate the trajectory. I can't talk too much about that. I have looked at it, but really have never used it. Now, as I said earlier, for today's video, I'm going to shift gears away from the 5.56. I'm going to be looking at the 308 Winchester. And I'm doing that particularly, number one, as I already stated, because it kind of has more, I'll call it, interesting trajectory out 700, 800, sometimes 900 yards, based on the type of bullet that you're using. And I also have a lot of experience with these 168 grain bullets, all different sorts. And we're going to be specifically looking at the 168 grain Sierra Match King. And this bullet was chosen because it is one of those that exists in the library for the Hornady Fordorf app. They have a tremendous number of different bullets. Yes, a lot of Hornady bullets, some Sierras, Bergers, and so on and so forth that are all available, already ready for you to make use of. I did a video a number of years ago. I looked at the Lapua 6DOF and haven't really used it much over the last couple of years. And the reason I don't use it is because it's only available for Lapua bullets. If you happen to be using Lapua bullets, fantastic. Go ahead and try it out. But I'm not using Lapua bullets for any of my examples in this season of extreme reloading, so I can't use it. We are going to be comparing our dope tables between Hornady Fordorf and Ballistic PRS. Now, by the way, DOPE is an acronym, and that stands for, normally, data observed from previous engagements, or sometimes drop observed in previous engagements. Just a little bit of FYI for you there. Anyway, let's go ahead and jump into these trajectory or dope tables and take a look at them. What we're looking at here is the trajectories for that 168 grain Sierra Match King bullet that I already mentioned at a 60-degree ambient temperature condition. We've calculated this from 100 yards out to 1,000 yards for the Hornady Fordorf and 100 yards out to 850 yards using Ballistic PRS. Now, why did I not calculate out to 1,000 yards with the Ballistic PRS? Well, it's because the way that that is set up, once we enter the transonic zone, about 1,300 feet per second, transonic zone, that's the speed of sound, 1,100 feet per second at this altitude, plus or minus 20%. So once that bullet enters that, Ballistic PRS, the way I have it set up, it does not calculate trajectories for you at that point. So what we know by looking at this table is at that point right there, between 850 and 900 yards, we're looking at this in 50-yard increments, that's where it hits the transonic zone. Now, what's really interesting is let's take a look at the difference between these two solvers. One, you'll notice that they're really, really similar. I mean, extremely similar. You might say, well, hold on, once you get down there to about 700 yards, they differ by about, well, 0.19 MOA, or let's just say 0.2 MOA. Now consider this, though. That's still not even one click on my scope. We could say, yes, that should be a click. Okay, fine. But it's not. See, it's not a full click at that point. That's really interesting. And the reason I say that is because the Ballistic PRS is based on a G1 ballistic coefficient. And that's a really, really old design, a Gavre function from just after the Civil War. Now, you may have heard that the Fordorf, which doesn't even use ballistic coefficient, it's a solver modeled on that particular bullet. And a tremendous number of calculations measurements made on that bullet literally as it is flying through the air using sophisticated Doppler radar. But what's interesting and what's curious is it didn't make much difference. Hornady says there's 400 plus parameters that go into the Ford-Off model. I believe that that's the case. But you know, I've done a lot of scientific modeling over the years, and one of the tenets to a model when you start developing a model, whatever you're trying to model, is number one, you want to identify the variables that influence the problem, whatever you're trying to solve or model for. Okay, so what are all the variables that could affect the flight of that bullet and its trajectory from point A, the muzzle, to point B, its point of impact, wherever that happens to be. And you know, obviously, it is going to be the shape of that bullet, its muzzle velocity, and wind conditions, all these other things that we talked about. But there's 400 and some different variables built into the Ford-Off. Well, in the modeling world, what we like to do, what we need to do, is we do what's called a data reduction exercise. And that is frequently done using what's called principal components analysis. We'll pull in all the different sources of data, the variables that influence that problem. We reduce all model variables to include only the primary driver variables necessary to correctly solve the problem. Normally, only 3 or 4 primary driver variables are needed to explain 95 to 99% of total variability and arrive at a correct solution. So I wouldn't doubt that even though there are 400 and some variables involved in the equation, that the answer is being controlled by a very small number of variables, probably 3 or 4. Now let's take a look at another table. This table that you're looking at right now, it looks really similar, except notice that this is for temperature conditions at 90 degrees Fahrenheit. And look at that differences column. We're seeing large differences. In fact, at 900 yards, it is 1.26 MOA difference between the Hornady Ford-Off and the ballistic PRS solver. That's 5 clicks on my quarter MOA scope. Now, what's interesting here is that the estimated muzzle velocity at 90 degrees Fahrenheit for the Ford-Off, I checked off that little box that says, include temperature compensated and temperature variable powders, and I chose Varget as the powder and all this good stuff. Well, it estimated that the muzzle velocity would be 2,588 feet per second. But I have chronographed the muzzle velocities for this bullet, and all the way from 0 to 60, 70, all the way through 100 degrees. And the muzzle velocity at 90 degrees is 2,618 feet per second. So if I go back and I plug a known muzzle velocity, 2,618 feet per second, into the Ford-Off, here's what we get. Now notice that the differences are not so great. However, they are larger than with the 60 degree ambient temperature conditions. And we have a range from about 700 out to, again, starting at 700 out to about 900 yards. That's when it goes transonic. We have 1 and then 2 clicks of difference. But elevation is not the only part that we're interested in as shooters. And in fact, as we shoot further and further and further, that wind effect becomes increasingly important. So let's go ahead and take a look at the wind calculations, comparing again Hornady Ford-Off to the ballistic PRS solver. And what we're seeing here is, again, pretty similar results for a 10 mile per hour perfect crosswind. Now that's always assuming it's a nice steady 10 mile per hour wind, and from about 450 yards all the way out to 800 so yards, again we are looking at a click of difference and approaching even 2 clicks of difference. Now one thing that's interesting about Hornady-Fordoff is it also includes the interactive effects of wind on elevation. And that's a real effect, no doubt about it. If you've never heard of that, look up the Bernoulli effect, right? So the direction that the wind is blowing will not only move that bullet laterally, or let's just say horizontally, it will also influence and move that bullet vertically. So there's that interactive effect. Ballistic PRS does not do that. It's not that sophisticated. Hornady-Fordoff does do that. Now, the interesting thing about wind, however, is that, and I did an experiment on this years ago, there has never been a condition where the wind is actually uniform from my location to the target. Well, maybe out to 100 yards, maybe out to 200 yards. But when this stuff really starts becoming important, 4, 5, 6, 7, 800, whatever, long-range shooting, it's not going to be uniform. It won't be uniform in velocity, and it sometimes actually switches. We have actually recorded that over a long range, and we've seen where the wind may be blowing, let's say, right to left from 0 to 200 and 300 yards, but then all of a sudden at about 450, it's coming back, it's swirling back in the other direction. That is really, really difficult to model, extremely difficult to model. And understand this, the wind velocity at ground level or near ground level is quite a bit lower than it is when we get to the top of that trajectory, right? That wind is going faster at higher velocity or higher altitudes, even just 10, 12, 20 meters, let's say above ground, we do see a measurable difference in wind velocity. That is really, really complicated stuff and very, very difficult to model. So which of these drop tables or dope tables am I going to use? Well, I'm going to use the one that's right, the one that is correct. How do I know which one is correct? And this is where it becomes really, really important. Don't put all your eggs into that table or into an app, because there can be differences. There can be errors in those things. And you've got to do what we call true your dope. Truth it. Validate it. So you're going to have to do some shooting, right? Great example. I calculated, again using Hornady-Fordoff, I calculated a nice drop table for my 6.5 Grendel shooting factory Hornady Black. Very good ammo, 123 grain bullets, shoot quite nicely, quite precisely. In my Grendel rifle, I actually determined the muzzle velocity. I didn't go with the muzzle velocities listed on the box. And then I calculated this drop table. Well, I've been out shooting 200 yards. Darn it, it's off by a full 2 clicks. Now this is a mil-based, so it's 2/10 of a mil. When I shot recently, just this last weekend, out at 350 yards, this table suggests or tells me to click 1.9 mils, in other words, 19 clicks, but when I'm shooting it, I can see I'm going over the top. I ended up, after making my adjustments, I ended up adjusting only 12 clicks. That's a 7-click, 7/10 of a mil difference. So you gotta true that dope. You gotta truth it, validate it in the field. Now when we're looking at the difference again between Hornady-Fordoff ballistic PRS, maybe the shooter's calculator, maybe a Lapua, whatever, it actually is pretty darn difficult to say, oh, this one is really the one that's most accurate, that one is no good, or whatever. It's really difficult to do that, especially at long range. And here's why. When we're talking about differences of only a click or two, right? Only a click or two of difference between one solver and another solver, how do you know if that difference was or wasn't you? I mean, are you, as shooters, are we really that good at 700 yards to know that I actually put that round dead on that bullseye? When that reticle, when I squeezed it, it was absolutely dead in that bullseye. I couldn't have been off just that little bit, which then made it look like this solver worked better versus that solver. And what's the dispersion on my ammunition? You shoot a good 5-shot, 10-shot group, and you look at the dispersion of that group on paper, I bet you'd have an argument to say that ballistic PRS or 4DOF or 6DOF, yeah, whatever. My favorite ballistic software worked best. Really, really hard to do. But if you are going to shoot long range, if you are going to shoot precision, you've got to start with a drop table, a dope table. You've got to start with that. And then you need to true it, true the dope. In other words, validate it. You can't forget that part. Once you have that validated and you know it is spot on out to 700 yards, 800, whatever, then you got it, right? Then you've got it. Don't forget temperature. Yeah, temperature plays a role. This is all part of this whole process. That's kind of the fun stuff of what we're doing. We got a great load. We proved it out to 100 yards. Very precise. Shooting wonderfully for us. Now we're going to stretch it out, and we're going to use Hornady 4DOF or whatever. We're going to validate it, and I got it. Now I can have some real fun shooting this rifle at long range. Well, before we wrap it up, if you really want to know, if you really want to make me make a decision about which of these pieces of software or apps do I think is going to be the one to use, I guess I would, if I had to make a decision, I would choose the Hornady 4DOF because I like the fact that it has those interactive effects of wind built into the model. And I think that that's excellent. Hornady's got an awful lot of bullets already built into that. We don't even have to rely upon a BC estimate. But there are other pieces of software that they're really so good also. So there we have it. I hope you've enjoyed this episode of Extreme Reloading. This is our season finale, but we'll be back next season, and we're going to focus on reloading for the 300 PRC, and that's my Barrett MRAD rifle. See you then.